Okay, we're back to look at this specific example. This is called an SIRS model. So typical epidemic models are maybe called SIR models. You may have heard of this, where S stands for susceptible, I stands for infected, and R stands for recovered or removed. So it means you have a population of individuals, and with respect to some illness or some disease, they can be susceptible first, and then they may transition to being infected, and then from infected, you can be recovered or stay infected. And then once you're recovered, this SIRS says that you can go back to being susceptible. The typical kind of general term SIR is used because for some illnesses, once you're recovered, you can never get it again, right? Like a lot of viruses. So we're going to do an SIRS model and take a look at what that is. So here are the specifics. So S of T is the number of susceptible individuals. I of T is the number of infected, and R of T is the recovered. So we assume the number of individuals is constant, so S plus I plus R is equal to some fixed tau. Let's also assume that the rate of transmission of the disease is proportional to the product of susceptible times infected. Okay, let's read through all these and we'll write equations. So the rate at which infected individuals recover is proportional to the number that are infected. So there's going to be some parameter here for the proportionality and here. And then recovered individuals lose their immunity and become susceptible again to the disease at a rate that's proportional to the number that are recovered. Okay, so this would be an example of this type of model would be something like a bacterial illness like malaria or tuberculosis, where you could be susceptible, you can get infected, you have TB, you cough, someone can get TB from you. Once you're recovered though, if someone else coughs on you, you can get TB again, right? So let's write out a system of equations that accounts for these. So we have 3 facts about the rates of change of susceptible, infected, and recovered. And here's how I would try and kind of put this information together. So transmission of the disease, the first point, is proportional to the product of susceptible and infected. That means the way that people leave the group of being susceptible and go to infected is there has to be some term that has an S times an I and a proportionality constant. I'm going to call that one beta. So you leave susceptible, so beta SI individuals leave, and they show up in the infected bin. Okay, hopefully that makes sense. The way that you leave being infected is that you recover. The number who recover is just proportional to the number who are infected. I'm going to call the proportionality constant alpha, and then those become, it's a minus alpha up here because I'm taking them out of the pool of I's and putting them into the pool of R's. The way that you stop being recovered is that some proportion of the recovered individuals become susceptible again, right? So let's say minus, we'll call mu the proportionality constant, R in the R equation, and I'm going to add those individuals back upstairs in the S equation. So that number of individuals becomes susceptible again. Since the way that we kind of talked about the balances here presupposes that the number of individuals don't change, right? You started in susceptible, you can either stay there or you can move to infected. And the only people who can get into susceptible, for example, come from recovered. But let's just verify that the sum of all these rates is equal to 0. That means the number of individuals isn't changing. So i.e. number of people is constant, right? So minus beta Si plus mu R plus beta Si minus alpha I plus alpha I minus mu R. Well, that should be clear. That is equal to 0. Check. Great. So we have 3 equations with 3 unknowns, but we also have this fact that we actually just verified, that the number of individuals doesn't change, and tau the number of individuals that we're looking at may be fixed. So we can actually get rid of one of the variables and we'll just have a two-dimensional system. So that'll be nice. Let's get rid of r by noticing that r is tau minus s minus I. So the first equation becomes s prime is minus beta si plus mu times tau minus s, minus an I. The second equation never had an r, so it's just beta si minus alpha I. So we went from these three equations upstairs to these two equations downstairs. And let's remember, so maybe we'll write it up here. So alpha is a proportion of individuals that recover. So this is, let's say, a recovery parameter. Beta is a number of individuals that become infected. Infection parameter. And mu is the number of individuals that become susceptible again. So we'll say that it's like re-susceptible. Okay, just remember what those mean physically. Okay, excellent. So let's consider this 2D system with some real numbers here. We're on page 6 of the notes. So the specific case is that beta is 1, alpha is 0.5, mu is 0.5, and tau is 1. And so the system looks like these two equations here, where the population is measured in the millions. So let's determine all equilibria and the stability properties of each. So just like what we did for the example before, but now we can have some sort of physical interpretation for the results that we find. Okay, so the second equation looks like, the second equation is, if I factor out the I and s minus a half is equal to 0. So if I let I is equal to 0, the first equation up here becomes, well, 0 and then 0.5 times 1 minus s is equal to 0, which implies s is equal to 1. So I have an equilibrium at s and 0. Or sorry, s is equal to 1 and I is equal to 0, which is, I'll write si to put a kind of fine point on it here. The other condition here is, what if I let, not I, what if I let s is equal to a half? And now go back to my first equation, plug in and see what I get, right? So now I have minus 1/2 I plus 1/2, 1 minus a half minus I. We can simplify that a bit, right? 2 minus a half i's. So minus I, oh, that's not the neatest handwriting in the world. Hopefully that's more readable. Minus I, and then it's 1 minus a half, so a half times another half, plus a quarter is equal to 0. So this means I have an equilibrium at s is equal to 1/2 and I is equal to 1/4. Cool. 2 equilibria. These guys here. So let's find the Jacobian, plug in the equilibria, and look at the eigenvalues of the Jacobian at these points for an understanding of the linear system, and then use the theorem to extend that to the nonlinear system. So the Jacobian derivative of the first equation with respect to s, minus I minus 0.5. With respect to I, minus s minus 0.5. Second equation with respect to s is I minus 0.5. Oh wait, no, just just this. And with respect to I is going to be S minus 0.5. Is that right? That looks good. Okay. So the Jacobian at 1, 0. 1 minus a half is minus 3/2. 0 minus a half is minus 1/2. I is 0. S is 1, so 1/2. This implies I's at 1/2 and minus 3/2. So this guy greater than 0 implies that 1, 0 is an unstable equilibrium. Okay, so what does that mean? To be unstable, so this was the number of susceptible, this is the number of infected. If I start a little bit away from this equilibrium, then the solution blows up. So it means if I start with no one infected, fine. If there's even a small number of individual infected, the infection spreads. If even a small number of people are infected, the illness spreads. Okay, great. Other Jacobian, the other equilibrium. So at, what is it, 1/4? 1 minus, or 1/2, 1/4. Excuse me. So I is 1/4. This becomes minus 3/4 in the 1, 1 position. S is 1/2, so minus 1. I is 1/4, and S is 1/2, so this guy is 0. Is that right? That looks like it. So the eigenvalues we don't know, so we'll compute lambda plus 3/4 plus 1 minus 1/4 lambda. So that's lambda squared plus 3/4 lambda minus minus. So plus 1/4 is equal to 0. So lambda is negative b plus or minus the square root of b squared minus 4 times a times c, so 1 all over 2a. I don't even have to compute this. All I notice that this number is less than 1, so when I square it, it's going to be smaller, so what's under the radical is going to be negative, so this is going to be imaginary. So this is going to look like minus 3/8 plus or minus something imaginary. That means that the real part here is less than 0. So what does that mean? That means that this equilibrium, so since real part of the eigenvalues is less than 0, this equilibrium 1/2, 1/4 is locally asymptotically stable. So solutions should go towards it. Okay, hopefully that is clear. So that would be how we look at an example where we knew what some of the parameters were. Let's go back to our kind of general equation here and try and explore it more, see what the parameters mean. Okay, so we didn't say this before, but we should assume that alpha and beta and mu are all positive. Whoops. They're all positive numbers, these proportionality constants. And also, I guess this kind of goes without saying, S, I, and R have to all be positive too, right? You can't have a negative number of people in any of these categories. So that supports the positivity of these different parameters. Okay, so we have this system. It says the number 1 says show that the system has 2 equilibria given by these 2 here. So if I want to set these two equations up here equal to 0, the second equation is beta si minus alpha I is equal, I can factor out that I, right? So it's beta s minus alpha is equal to 0, which has two solutions. I is equal to 0. That's the first one. And then if I plug that into the first equation, I have 0 plus mu times tau minus the number susceptible, right? And that's going to be equal to 0 to solve, which implies that S should be tau. So 1 equilibrium at tau 0, check. The other condition here to make the second equation negative is to let S be equal to what? Alpha over beta. When I plug that into the first equation, minus beta, so the betas cancel, so I'm left with minus alpha I plus mu times tau minus alpha over beta minus I is equal to 0. Oh, good gracious. Was I writing this whole time and you couldn't see? Oh, I hope not. I'm sorry. Okay, so that was the first equation. Now here's the second equation. Okay. So we can solve this for I, and we get this solution. Is that clear? Let's see. So I have I is minus alpha minus mu, minus mu, that's how you write a mu, on this side, and then the other side is equal to mu alpha over beta minus tau. And then, yeah, so we divide by this, so we have the negative signs that flip it, and then mu tau minus alpha over beta, and then alpha plus mu. Great. Okay, so these are our two equilibria. Perfect. So when is the first equilibrium solution unstable? When is it stable? And then this has this kind of leading question. Explain why alpha over beta is called the threshold level of the disease. Well, let's look at the stability property. It's maybe a less cryptic way of talking about this. We need the Jacobian of the system first, right? We didn't do that in general, I guess. So the derivative with respect to S minus beta I minus mu minus beta S minus mu with respect to S, beta I with respect to I, beta S minus alpha. Okay, same form as before. So let's say what's the Jacobian at tau 0. Okay, so we have minus mu, the i's all go to 0. The S is minus beta tau minus mu and beta tau minus alpha, these guys, right? It's a triangular matrix, so I know the eigenvalues just by reading them off the diagonal. The eigenvalues are minus mu and beta tau minus alpha. Minus mu is always less than 0, right? Since mu is always positive. So if I want to talk about the stability of this equilibrium, what I need to look at is where this guy is positive and where it's negative. So what I'm going to notice is that beta tau minus alpha is going to be less than 0. Let's see, it means that tau less than alpha over beta gives this guy, maybe not gives, let's say makes this guy a what? If this guy's negative and this guy's negative, a locally asymptotically stable equilibrium. Likewise, if this is positive, then tau is greater than alpha over beta. That condition makes this guy an unstable equilibrium. So why alpha over beta is called a threshold level, because it means this is going to be the parameter that will determine whether or not this is going to be stable or unstable. And so if we think back to what alpha and beta mean, let's go back here. So alpha was like a recovery parameter, beta is like an infection parameter. So if alpha over beta, if you're recovering way, way faster than you're getting infected, then this may actually be a locally asymptotically stable equilibrium. So in the parameters that we chose for the example on page 6, this wasn't the case, right? Because if you don't recover fast enough that it can't spread, then it's unstable. And that's the case here. Now this says if this is bigger, if this ratio is easier to kind of be overcome for a certain population level, then your recovery time isn't fast enough. And so you have an unstable equilibrium instead. That's there. Okay, so hopefully that makes sense. So next we want to look at the other equilibriums. This is the equilibrium tau 0. We want to look at this more exciting equilibrium and its stability properties. So to do this same procedure and find the eigenvalues with this kind of crazy expression, or just let's say ridiculous expression with a bunch of parameters, the math is going to be, you know, the arithmetic, say, is going to be really incomprehensible to find this greater than or less than conditions. So what we need to do is have a linear algebra trick. So let's have a brief digression for tricks in linear algebra, which is here. Okay, so let's consider a 2x2 matrix. You may remember this from linear algebra. This is like so useful. It's not only for 2x2, by the way. But if we have a 2x2, it has two eigenvalues. They may be complex, they may be repeated, it's fine. I don't know if you remember this, but the determinant is the product of the eigenvalues, and the trace is the sum of the eigenvalues. So we can show that really quickly. So maybe if you don't remember it, it'll kind of stick in your head more. This is a totally useful thing because we can use this to determine signs of eigenvalues without finding their actual values, if we don't care about what the values actually are. So remember, eigenvalues minus A, minus B, minus C, alpha, D, not alpha, lambda. So we have lambda, let's see if we can do it in one step, lambda squared minus A plus D lambda plus AD, and then minus, 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 minus BC is equal to 0. That's the quadratic to solve. Fine. So we have lambda 1 and 2, they're going to be negative b plus or minus the square root of b squared minus 4 AC all over 2a. Okay. So that's just, you know, kind of the form real stuff plus or minus some other stuff, which may be real or it may be imaginary. Let's consider the first thing. What's lambda 1 plus lambda 2? So all the stuff under the radical, we have the positive and then we also have the negative, right? We have AD over 2 plus radical some junk over 2 plus A plus D over 2 minus some radical with some junk over 2. So these guys cancel and I just get A plus D. What's A plus D? It's the trace. Easy, right? Second fact, what's the product? Lambda 1, oops, times lambda 2. What's that going to look like? So if I have, how can I think of this? Kind of brief, I have a number, this is A plus B, right? So I'm going to get, when I multiply these out, a squared. Can I do this in like a shorthand? Be this chunk squared minus this chunk squared, right? Here, I'm gonna call this, we need other characters. Let's call this n plus or minus m. So this is gonna look like n plus m times n minus m, right? So it's n squared plus nm minus nm minus m squared. Hopefully that's really clear. I don't want to beat a dead horse. I just don't want it to be confusing. So this should be the first guy squared, a plus d squared over 4 minus the second guy squared. Well, the radical, everything under it now is not under any radical. And then it's 2 squared, so 4. Great. So this cancels with this. The 4's cancel, and I'm left with AD minus BC, which is the determinant of A. Check. Okay, so now we know the determinant is the product of the eigenvalues and the trace is the sum. Box around them. These are like super important things to remember. Great. Okay, so now the thing we want to conclude. Let's let the determinant of A be positive and the trace of A be negative. Okay. So if I have two real eigenvalues, for real eigenvalues, right? So the determinant of A is going to be lambda 1, lambda 2, and we said that we're assuming that that's positive. That means they are the same sign, right? They're both negative or they're both positive. Trace of A, lambda 1 plus lambda 2 less than 0 means they better both be negative. Okay, so that means the real parts are of course negative because they're all real. For complex eigenvalues, the trace is going to be, so this was alpha plus or minus I beta. If it's a 2 by 2, it has to be complex conjugate pair, right? So the trace is going to be 2 alpha because the I beta is like a plus and minus. We said that we assume that the trace is negative. Well, that implies that alpha is negative. Alpha is, of course, the real part. So the real parts are negative. So we can conclude what it says up here, what it wants us to conclude, which is that if the determinant is greater than 0 and the trace is less than 0, then the real parts of these guys are negative. So that fact is only good for a 2 by 2. Specifically, right? Because I'm looking at like this sign of the product of 2 numbers. If I have 3 numbers, I can't say when I multiply them together that they're the same sign, just because this is positive, because of course negative 1 times negative 1 times negative 1 is negative. So that's a fact for 2 by 2s, but these are facts that actually hold for larger matrices. Okay, anyway, that's fine. We're in a 2 by 2 system, so all of this is useful. Let's get back to the SIRS model that we were considering before. So let's use that result to show that the second equilibrium here is locally asymptotically stable when we have the condition that, that tau is positive. Okay, so let's take a look. We have to go back to the Jacobian, which I'm going to put it kind of upstairs here. Can you see everything at once? Oh, we can do it. Here we go. That's the Jacobian. And, well, I guess you could just look at it on your piece of paper. Otherwise, we're not going to have enough room. Okay, so the Jacobian at alpha over beta, and then mu tau minus alpha over beta, alpha plus mu. So I'm going to plug these guys in. Let's see. It's kind of like ugly to plug in. So let's just keep it in this form for now. We're going to be able to do it in this form. Minus, and then beta s minus alpha. Okay, let's try and just look at it with this. So what's the determinant here? It's going to be this times this. So minus beta squared si plus alpha beta I minus mu beta s plus mu alpha. And then minus, oh gosh, I'm reading what you can't see, sorry. Minus, well, there's a minus and there's going to be these pluses. So beta squared si plus mu beta I. Did I get the signs right? I think so. I think that's okay. So this guy cancels with this guy. Mu beta s anything else cancel here? Oh, well, the other thing is, we also assume that this is the case, right? So that means that this here oh no, that doesn't help. Do I know anything else? Oh, excuse me. We know that S is equal to alpha over beta. That's what we know. Of course, we have to use the fact about the equilibrium. So that means that this term here, S beta, is equal to alpha. So these guys also cancel. Okay, great. So I can simplify this a little bit, right? So that means I can write this as beta I, and then what? Plus mu plus alpha, or times mu plus alpha. Okay, beta is always positive, mu is always positive, alpha and I are always positive. Check. And the trace of J, the trace of the Jacobian, what's that going to be? That's going to be minus beta I minus mu plus beta S minus alpha. So again, we know that beta S is equal to alpha, so these guys cancel. So I'm just left with minus beta I and minus mu. All those numbers should be positives. They have negatives in front of them, so they're all less than 0. So what does that mean? That means that that equilibrium here, the equilibrium at alpha over beta, and then mu tau minus alpha over beta, alpha plus mu, should have 2 negative eigenvalues. So it should be locally asymptotically stable when, whoops, tau is greater than alpha over beta. Does that look good? I think so. So hopefully this kind of taught us how we can study nonlinear systems, the stability of their equilibria, systems of equations, and then we learned how to build an epidemic model and study its equilibria to understand stability of those different places in the system, say. This, by the way, this trick of finding the signs of equilibrium without, or sorry, the signs of eigenvalues without actually finding the eigenvalues It's a super, super useful trick. So I wanted to show this to you, especially today. All right, that's it.